Right now, 2.5 miles beneath one of America's most visited national parks, a hidden cap of molten rock is breathing. Scientists just mapped it, and what they found changes everything we thought we knew about what sits beneath our feet. We will go inside the magma highways, the underground earthquakes no one detected for decades, the new hot spring that appeared out of nowhere in 2026, and the one scenario that terrifies every volcanologist alive. If you want more like this, subscribe. You will not want to miss where this goes. Brace yourselves. We begin. The year was 2015. A team of scientists pointed a seismic scanner straight down into the ground beneath Yellowstone National Park. They expected to confirm what they already knew. They found something that made them question every map, every model, and every assumption they had built over decades of research. Yellowstone sits in Wyoming, and most people know it as a park full of geysers and hot springs. Old Faithful shoots boiling water into the air every 90 minutes like clockwork. The ground in some places feels warm through your shoes. Mud pots bubble at the surface like thick soup on a stove. For most visitors, it reads as a natural wonder, beautiful and strange. Scientists knew the park sat above a supervolcano. They had known that for decades. They had mapped a shallow magma chamber sitting a few miles underground, a reservoir of partially melted rock that powered all the heat activity visible at the surface. That chamber was already enormous by any measure, big enough to fill the Grand Canyon twice over. Geologists had studied it, monitored it, and felt reasonably confident they understood the basic structure of what lay below. Then the new scan came back. Hidden beneath the known shallow chamber, buried deeper than any previous instrument had reached clearly, sat a second reservoir, a massive one. A chamber so large it could fill the Grand Canyon 11 times over. 11! The shallow chamber they had spent years studying was the small one. The team stared at the data, then they ran it again. The deep reservoir stretched between 12 and 31 miles underground, a thick column of partially melted basalt rock, bridging the gap between the molten mantle far below and the upper crust near the surface. It had been sitting there the entire time, undetected, quietly connected to everything above it. What made this discovery so significant was the connection. The shallow chamber and the deep chamber were linked, forming a continuous system of volcanic plumbing that stretched from deep in the earth all the way up toward the surface. Pressure generated at the bottom could travel upward through that system. Heat generated miles below could feed the reservoirs above. The two chambers acted less like separate containers and more like floors in the same building, connected by the same staircase. Geologists had to revise every estimate they had made about the size of the Yellowstone system. The fuel supply was far greater than the model showed. The depth of the system was far more significant, and the speed at which pressure could move from the deep reservoir to the shallow one was faster than anyone had calculated. Here is what made the room go quiet. Scientists realized they had been monitoring only the top floor of a much taller structure. Every alarm threshold, every pressure model, every evacuation timeline they had ever drawn up was based on partial information. The park kept steaming. Old Faithful kept erupting on schedule. Tourists kept walking the boardwalks. But underground, the picture had grown dramatically larger and dramatically more complex. And that second chamber was only the first surprise. Because sitting above it all, just 2.5 miles beneath the surface, something else had been hiding. Something that no instrument had clearly identified before. A cap. A volatile, pressurized, actively breathing cap. And when researchers finally got a good look at it, the story shifted again. Most people imagine solid ground as something permanent. You stand on it, build on it, drive across it. It holds. But the deeper you go, the stranger the rules become, and Yellowstone breaks almost all of them. The outer layer of the Earth, the part everything living sits on, is called the crust. Under continents, it runs roughly 25 miles thick on average. Think of it as the hard shell of a hard-boiled egg. Below it sits the mantle, a layer of rock so hot and under so much pressure that it can actually flow slowly, the way thick wax moves when it gets warm. Below that, thousands of miles down, sits the core, dense and burning. Under most of the United States, that basic structure holds more or less true. The crust sits stable. The mantle moves slowly beneath it. Heat rises gradually. Nothing dramatic happens on a human timescale. Yellowstone operates under a different set of rules entirely. Beneath the park, a column of superheated rock rises from deep in the mantle toward the surface. Geologists call it a hotspot. Picture a blowtorch aimed straight up at the underside of the crust from hundreds of miles below. The rock directly above that blowtorch gets stretched, thinned, fractured, and partially melted. The crust above Yellowstone measures only about 6 miles thick in some places. Everywhere else in the region it runs much deeper. Here, the heat has eaten it thin. That thinning matters enormously. The thinner the crust, the less distance there is between the molten rock below and the surface above. In most places on Earth, you would have to drill dozens of miles before hitting anything molten. At Yellowstone, the gap between you and liquid rock is short enough to be terrifying when you picture it. And the rock itself behaves differently here. Under extreme heat and pressure, rock that would normally stay solid begins to act like something between a sponge and a sponge soaked in liquid. Tiny cracks form. Water and gas seep in. Minerals melt and recrystallize. The crust above the magma chambers is fractured from the inside, stretched by centuries of heat, pushing upward from below. Scientists measuring the ground at Yellowstone have discovered that it rises and falls. Literally. The surface of the caldera, the giant depression left by the last major eruption, moves up when magma or hydrothermal fluids push upward from below and sinks back down when pressure releases. This movement is slow, usually inches over months or years, but it is real and measurable, and it is tracked by a network of sensors planted across the park. The magma below is not fully liquid. It is more like a slushy mixture, solid rock crystals suspended in a smaller fraction of molten material, with pockets of superheated gas and water mixed throughout. The exact percentage of melt inside the chambers determines how dangerous the system is at any given time. Higher melt percentages mean the system moves faster, pressurizes quicker, and reacts more dramatically to any trigger. Right now, sensors suggest the melt fraction inside the shallow chamber sits at somewhere between 5 and 15%, low enough that an eruption is far away, high enough that the system remains very much alive, and what keeps that system from tipping over the edge, from reaching the point where pressure overwhelms the rock above it, is something scientists only recently identified: a cap. A strange, volatile, actively venting cap sitting 2.5 miles down. Keep going. Because what this cap actually does will surprise you. 2.5 miles. That is roughly the height of 10 Empire State Buildings stacked on top of each other. In Yellowstone, that is also the distance between the surface and a layer of rock and fluid that researchers from Rice University and the University of Utah identified in April of 2025. They called it a volatile-rich cap. Everyone else called it something far more unsettling: a lid on a pressure cooker. The cap sits directly above the shallow magma chamber. It formed over long periods of time as magma rose from below, cooled slightly near the top of the reservoir, and left behind a concentrated layer of minerals, dissolved gases, and supercritical water. The material in this layer is dense, pressurized, and chemically different from both the magma below and the fractured rock above. What makes it remarkable is what it does. As magma in the chamber below heats up and slowly rises, the pressure inside the cap increases. The dissolved carbon dioxide and water inside the magma begin to separate out, forming bubbles. The same process happens in a can of soda when you crack the tab. Pressure drops, gas comes out of solution, and bubbles form rapidly. Inside a sealed container, that would mean a buildup of pressure so intense it could rupture the walls. But the cap handles it differently. The bubbles rise through the cap layer, squeeze through the small cracks and porous spaces in the rock above, and escape upward through the crust. They eventually reach the surface as steam vents, hot springs and gas seeps scattered across the park. The system vents the pressure before it can accumulate. Researchers described it as the volcano breathing. Pressure builds below, rises through the cap, escapes through cracks above, and the system stabilizes again. A slow, constant inhale and exhale happening miles underground, completely invisible to the 3 million tourists walking the boardwalks every year. The cap is effective, but it has limits. The escape routes, the tiny cracks and pores in the rock above the cap, can get clogged. Minerals carried upward by the hot fluids can crystallize inside those channels, slowly sealing them shut the way plaque builds up inside an artery. When that happens, the pressure has nowhere to go. The slow breathing stops. The cap begins to hold rather than vent. Scientists do not yet know exactly how long the system can hold before the pressure surpasses what the cap and the rock above it can contain. They have models. The models have large margins of error. What they do know is that the cap is currently functioning, the cracks are currently open, and the system is currently venting. For now. The discovery of the cap also raised a question that nobody had fully answered before. If the cap is managing pressure this efficiently, how is anyone supposed to detect the moment it starts to fail? The surface changes that would signal a problem underground are subtle, easy to miss, and in some cases, by the time they are visible, the window for response has already narrowed. Something appeared at the surface in early 2026 that suggested the underground plumbing was already shifting. But before we get there, you need to understand what the fluid inside that cap actually is, because it behaves like nothing that exists anywhere on the surface of the Earth. Pour water into a pot and heat it. At 212 degrees Fahrenheit it boils. It turns to steam. That transition, liquid to gas, is something every person on Earth learns before age 10. But take that same water and place it under extreme pressure, while heating it past a specific threshold, 705 degrees Fahrenheit, and something different happens. The water does not boil. The boundary between liquid and gas disappears entirely. The water becomes something that behaves like both at the same time. Scientists call it supercritical water, and under normal surface conditions it cannot exist. It requires pressure that only occurs miles underground. Inside the Yellowstone magma cap, the conditions are exactly right for it. The depth creates pressure. The magma below creates heat. The combination produces a fluid that is denser than steam, but flows like a gas, carrying dissolved minerals, silicate particles, and volcanic gases through the tiniest cracks in rock, the way water flows through a sponge. This matters because supercritical water behaves as an extraordinary transport system underground. It dissolves minerals that normal water cannot touch. It carries heat from the deep magma chambers toward the surface more efficiently than solid rock ever could. And when it rises high enough that the pressure drops, it flashes instantly into steam, releasing energy in a sudden burst. That flash transition is part of what drives geysers. Deep below Old Faithful, water heated by proximity to magma reaches supercritical conditions in the narrow underground channels. As it rises and the pressure above it decreases, it crosses back over the threshold and explodes into steam, driving the column of boiling water upward through the vent and into the air. The 90-minute eruption cycle you can set your watch by is actually a pressure recharge cycle for a supercritical water system working miles below the surface. The presence of supercritical water inside the cap also changes how scientists model what a destabilized system would look like. Normal water mixed with hot rock produces steam pressure. Supercritical water mixed with hot rock and volcanic gases produces something with significantly more energy behind it. When the transition from supercritical to gaseous state happens rapidly, the expansion is violent. Geologists compare it to a steam explosion, except the fuel is not just water. It is a mixture of water, carbon dioxide, and silicate-rich volcanic fluid, all transitioning phases at once. The rock sitting above the cap holds all of this in place. Fractured, porous, and riddled with small channels carved by millions of years of fluid movement, that rock acts as a filter and a pressure release valve simultaneously. Fluid moves through it. Gas escapes through it. The system vents continuously. But the minerals carried by the supercritical water deposit themselves inside those channels as conditions change. Silica, a mineral abundant in the magma below, crystallizes out of solution when temperatures drop slightly near the top of the cap. Over time, those crystallized deposits narrow the channels, slow the flow, begin to seal the escape routes. Scientists watching the surface found a clue that something in those channels had already shifted. A clue that showed up as a vivid blue pool of water in a place where only dry ground had existed before. That pool appeared in early 2026, and it was not a small change. Picture the biggest balloon you have ever seen. Now imagine it is buried 6 miles underground, slowly inflating. The rubber stretches. The pressure inside grows. If the balloon had no way to release air, eventually it would rupture. Violently. Yellowstone's magma system works on the same principle, scaled up to something almost impossible to picture. The difference between a catastrophic eruption and the park's current calm comes down to one mechanism: venting. Continuous, underground, invisible venting that has been happening for thousands of years without anyone realizing it was the thing holding the system together. Here is how it actually works. Deep in the magma chambers below, heat from the mantle keeps the rock partially molten. Dissolved gases, primarily carbon dioxide and water vapor, stay locked inside the magma the same way carbonation stays dissolved in a sealed soda bottle. While pressure stays high, the gas stays in solution. The magma stays thick and sluggish. As magma slowly pushes upward toward the cap layer, the pressure above it decreases. The gases begin separating out of the melt, forming bubbles. Tiny ones at first, then larger clusters as more of the dissolved material comes out of solution. Those bubbles rise faster than the magma around them because gas is lighter than molten rock. The bubbles reach the cap layer and enter it. The cap material, that dense zone of supercritical water and mineralized fluid sitting 2.5 miles down, acts as the first filter. Some of the gas dissolves back into the supercritical fluid. Some of it continues upward as bubbles, squeezing through the fractured rock above the cap and climbing toward the surface through channels carved by millions of years of fluid movement. At the surface, those escaping gases appear as steam rising from vents, as the sulfur smell that greets visitors near certain thermal features, as the steady release of carbon dioxide measured by sensors across the park. Scientists have calculated that Yellowstone releases between 45,000 and 60,000 tons of carbon dioxide per day through this natural venting system, every single day. That number is staggering, but it is also the reason scientists sleep at night. As long as the gas is escaping, pressure is not building. The system breathes out, the chamber pressure stabilizes, and the cycle continues. The problem is that the breathing is not guaranteed to continue. The same hydrothermal fluids that carry gas upward also carry dissolved silica, calcium, and other minerals. As those fluids cool while rising through the upper layers of rock, the minerals crystallize and deposit on the walls of the channels they flow through. Slowly the channels narrow. The breathing becomes more labored. If enough channels clog, the venting slows. Pressure inside the cap begins to rise. The balloon starts inflating with nowhere to release. Geologists monitor the gas output at the surface constantly. A drop in emissions could signal one of two things. Either the system is becoming less active, which means less magma pushing up from below, or it could mean the channels are closing and the gas has stopped escaping. Those two scenarios look the same from the surface. Telling them apart requires looking at the seismic data, the ground deformation readings, and the temperature changes in the hydrothermal features simultaneously. And in March of 2026, the ground started rising. The sensors picked it up first. Something was pushing upward from below. Something had changed in the plumbing. The ground beneath Yellowstone shakes constantly. That is a known fact, well documented, closely watched. Every year, scientists record somewhere between 1,000 and 3,000 earthquakes in the region. Most are tiny, far too small for any person to feel. They happen because the crust above the magma system is fractured and under stress, and because the movement of hydrothermal fluids through underground channels creates micro-vibrations in the rock. For decades, scientists categorized these quakes using standard seismic analysis. A computer system would detect a seismic signal, compare it to known earthquake signatures, and log it if it matched. The system worked well for anything above a certain size threshold. Anything smaller, or anything that looked slightly different from the expected patterns, got filtered out as noise. A team of researchers recently decided to go back and look at that noise. They fed decades of archived seismic recordings into an artificial intelligence model trained to recognize patterns too subtle for traditional analysis. The model did not look for what a typical earthquake was supposed to look like. It looked for any repeating, structured signal hidden inside the background noise of the data. It ran through years of recordings second by second. The results came back with 86,000 previously undetected earthquakes. 86,000 events that had been sitting in the data the entire time, invisible to every conventional method used to analyze them. Each of those hidden quakes represented a moment when rock fractured, shifted, or when fluid pushed through a channel with enough force to create a detectable vibration. Alone, each event was meaningless. A tiny crack in a rock 2 miles underground, a pocket of water forcing open a narrow passage, a crystal of silica breaking loose from a channel wall. Individually, the data meant nothing. Together, the 86,000 events told a story. When scientists mapped their locations, the hidden earthquakes did not scatter randomly across the region. They clustered. They traced specific pathways through the crust, connecting the shallow magma chamber to the surface, connecting the cap layer to the fractured rock above it, outlining the exact channels where hydrothermal fluids were actively moving. The map looked like the root system of an enormous tree. Branching pathways spreading outward and upward from the main chambers, with denser clusters where fluid movement was most active and thinner branches where the rock was more solid. The entire underground plumbing system, invisible to direct observation, had essentially drawn itself using the locations of its own microtremors. This was a significant shift in how scientists could monitor the system. Before, they tracked the earthquakes they could detect and guessed at the fluid pathways from surface observations. Now, they had a detailed map of the channels, the active zones, the places where pressure was moving most aggressively through the rock. The map also revealed something unexpected. Several of the densest clusters of hidden quakes appeared in areas where surface monitoring had previously shown very little activity. Regions of the park that looked calm from the outside were showing intense fluid movement underground. The surface and the subsurface were telling different stories. That gap between what the surface shows and what happens underground is exactly what makes the next discovery so important. Because when Chinese scientists published a paper in April of 2026, they revealed that the underground system was even more complex than the hidden earthquake map suggested. The heat source powering all of it did not rise straight up the way everyone had assumed for decades. When the team finished mapping the 86,000 hidden quakes, they printed the result. The image looked nothing like what seismic maps of most volcanic systems look like. Standard volcanic maps show relatively clean zones, a concentrated cluster of activity directly above the magma source, thinning out toward the edges. The Yellowstone map looked like someone had taken the root system of a 500-year-old oak tree and pressed it flat onto a page. Dense branching pathways spread outward from the central chambers in every direction, twisting, reconnecting, splitting again, and reaching toward the surface through dozens of separate routes. the denser the cluster of hidden quakes in any one area, the more active the fluid movement there. Each dot on the map represented a moment when hydrothermal fluid or gas forced its way through rock hard enough to create a detectable vibration. The regions with the thickest clusters were the most active fluid highways underground. Some of those highways ran straight up toward known thermal features at the surface. The cluster pathway underneath Old Faithful connected directly to the famous geyser above it, confirming what scientists already suspected about that vent's plumbing. The cluster pathways underneath the Norris Geyser Basin were dense and active, branching in ways that suggested a highly complex underground network of interconnected channels, rather than a simple straight pipe feeding the surface features. But several clusters appeared in places where no major surface features existed. Open meadows inside the park, stretches of seemingly ordinary forest, areas that visitors walk through without any sign of heat or hydrothermal activity nearby. Underground, those areas were some of the busiest fluid corridors in the entire system. The surface gave no indication. This pointed to something scientists had suspected, but never been able to quantify. A large portion of the pressure relief happening beneath Yellowstone occurs in the subsurface, between the magma cap and the upper rock layers, never reaching the surface at all. The system disperses energy through the rock itself, not just through the visible vents and geysers above. The map also showed areas of relative quiet, regions where the hidden quake density dropped sharply, where the rock appeared less fractured and the fluid movement less active. These quiet zones were the places where channels were either sealed, undeveloped, or blocked. Scientists flagged these regions for additional monitoring, because quiet zones in an otherwise active system can mean one of two things. Either the rock there is simply less fractured, or the channels there are clogged and pressure is building with nowhere to go. Cross-referencing the quiet zones with the ground deformation data added another layer. In one region of the caldera, a quiet seismic zone overlapped with a location showing subtle but measurable ground uplift. The surface was rising. The underground fluid channels in that same area showed reduced activity. Something was pressing upward from below in a zone where the normal venting pathways appeared partly blocked. The team marked the region for continued observation. What they did not yet know was that the pathway feeding all of these chambers, the deep pipeline connecting everything to the heat source far below, did not point straight down the way every textbook had described it. And when that discovery arrived, it forced a rethinking of the entire system from the ground up. Stand at Old Faithful on any given day, and you will watch it erupt roughly every 90 minutes. The water column climbs somewhere between 100 and 180 feet into the air, depending on how full the underground reservoir was when the pressure finally released. The crowd cheers. The steam drifts sideways in the wind. Then the ground goes quiet again, and the recharge cycle begins. Every one of those eruptions draws power from the same source. Approximately 3 to 8 miles beneath the surface sits the shallow magma chamber, the upper reservoir in Yellowstone's 2-stage underground system. This chamber holds a mixture of solid rock crystals, partially melted rock, and pockets of superheated fluid and gas. Scientists estimate that between 5 and 15% of the material inside it is actually molten at any given time. The rest is hot, partially crystallized rock sitting in a semi-solid state. That might sound like a low melt fraction, and in terms of eruption risk it is reassuring. A chamber with 5% melt behaves very differently from one with 50% melt. The higher the melt fraction, the more fluid the magma, the faster pressure can build, and the faster the system can move toward an eruptive state. At current estimates, the shallow chamber sits firmly in the non-eruptive range, but the chamber is still actively connected to the surface through an intricate system of cracks, channels, and hydrothermal pathways. The heat conducted upward from the partially molten rock heats groundwater that has seeped down through the upper crust from rain and snowmelt. That heated water fills reservoirs in the fractured rock above the chamber, pressurizes, and eventually forces its way upward through the narrow conduits connecting to the surface geysers. Old Faithful works on a specific rhythm because its underground plumbing has a specific volume. The conduit below it holds a set amount of water. Heat from below brings that water to the pressure point. Eruption clears the tube, recharge refills it, and the cycle repeats. The entire system functions like an underground piston, and the shallow magma chamber provides the constant heat source driving the piston. The same basic mechanism powers the more than 10,000 individual thermal features scattered across the park. Hot springs, mud pots, fumaroles, smaller geysers. Each one sits above a section of the same fractured, heat-saturated rock, drawing from the same heat source below. The differences in their behaviour come down to the exact shape and depth of their individual plumbing. What changed scientists' understanding in 2015 was the realisation that the shallow chamber they had been studying for decades was drawing its heat from below. It was not the primary fuel source, it was a relay station. The real fuel sat much deeper, in a reservoir 4.5 times larger than the shallow chamber, connected to it from below through a narrow bridge of partially molten rock. That deeper chamber had gone undetected because the instruments available before 2015 simply could not resolve the signal clearly enough at those depths. The data existed in pieces. A team at the University of Utah assembled those pieces into the first clear picture of a 2-story system, and everything geologists thought they knew about the scale of what sits beneath the park had to be revised upward. The shallow chamber was the part of the iceberg above water. What sat below it was the actual mass, the year 2015. A team at the University of Utah ran seismic data through a new imaging technique that could resolve structures deeper than anything previously attempted at Yellowstone. The shallow chamber appeared where expected, sitting between 3 and 8 miles underground, recognizable from decades of prior work. Below it, something else appeared. Something enormous. The deep magma chamber stretched from 12 miles underground down to roughly 31 miles. At its widest, it spanned the full width of the Yellowstone caldera and beyond. The volume of rock and magma held inside it dwarfed every previous estimate of the Yellowstone system's total fuel supply. If that chamber ever fully erupted, the material released would fill the Grand Canyon 11 times over. Scientists had not detected it before, because seismic imaging at those depths requires capturing signals that have bounced through miles of rock of varying density, temperature, and composition. The signal-to-noise problem is enormous. Earlier techniques smoothed out the details that revealed the deep chamber. The new imaging method, called ambient noise tomography, used seismic waves generated by natural sources, wind, ocean activity, distant earthquakes, and filtered them through Yellowstone's crust from hundreds of different angles simultaneously. The picture that emerged showed 2 distinct reservoirs sitting one above the other, connected at their interface. The deep chamber holds mostly basalt, a type of rock that melts at lower temperatures than the silica-rich rock in the shallow chamber above. Basalt magma is also less viscous, meaning it flows more easily. When the mantle plume below pushes heat upward, the basalt in the deep chamber melts first and most completely. That molten basalt then supplies heat to the underside of the shallow chamber above, warming the rhyolite-rich material there and maintaining the system's activity. The bridge between the 2 chambers is a narrow zone of partially molten rock where the 2 different magma types interact. This zone acts as a thermal and chemical exchange point. Heat from below transfers upward. Volatiles, gases like carbon dioxide and water vapour, rise from the deeper, hotter chamber into the shallower one above. Before 2015, scientists modelled Yellowstone's pressure dynamics using only the shallow chamber. The new discovery meant every model was missing the primary fuel supply. The deep chamber provides continuous thermal input to the shallow one. If the melt fraction in the deep chamber increased significantly, it would accelerate heating in the shallow chamber above it, potentially raising the melt fraction there faster than any model based only on surface observations would predict. The monitoring system at Yellowstone was designed with the shallow chamber as the primary concern. After 2015, scientists began the slow work of updating that system to account for the deeper structure, new sensors, new data interpretation frameworks, new thresholds. The work was not complete by 2026, and in 2026 new measurements from a completely different direction suggested the system feeding both chambers from below was far more complicated than even the two-chamber model described. The heat source rising from the mantle, the pipeline everyone had assumed pointed straight up, turned out to be tilted, branching, and connected to tectonic forces spread across the entire western United States. When that paper published, the scientists who read it had to update their models again. Think of two water balloons connected by a narrow tube. Squeeze the bottom balloon hard enough, and the pressure travels up the tube and pushes into the balloon above. If the top balloon has no way to release the extra pressure, it strains against its own walls. That is roughly how the connection between Yellowstone's deep and shallow magma chambers works. Except the balloons are miles wide, the tube between them is rock, and the timescales involved stretch from years to centuries. The bridge connecting the two chambers sits at a depth where temperature and pressure conditions allow rock to exist in a semi-molten state. Solid enough to hold structure, hot enough that portions of it remain fluid. Through this bridge, heat rises continuously from the larger chamber below into the smaller one above. The heat transfer is not explosive or sudden. It happens gradually, the way warmth spreads through a thick metal rod held over a flame. Basalt melting in the deep chamber releases heat upward into the bridge zone. That heat conducts into the underside of the shallow chamber, slowly raising the temperature of the rhyolite rock there. As the temperature rises, a slightly larger fraction of the shallow chamber's material melts. The melt fraction creeps upward, fractions of a percent at a time, over thousands of years. Alongside the heat, gases travel upward too. Carbon dioxide and water vapor, dissolved in the deep basalt magma, separate out as the magma rises and pressure decreases. Those gas bubbles rise through the bridge zone faster than the heat does, because gas moves more freely than thermal energy through semi-molten rock. They reach the underside of the shallow chamber and begin accumulating there. This is where things get more complex. In the shallow chamber, the rhyolite magma is more viscous than the basalt below. It is thicker, stickier, less able to let gas bubbles move through it freely. Bubbles that enter from below can get trapped inside the viscous melt, unable to rise and escape. As more gas accumulates inside the shallow chamber, the pressure inside it increases. The rock walls of the chamber flex outward slightly. The surface above rises in response. This is measurable. Ground deformation sensors at Yellowstone detect this flexing as the ground rises or falls over months and years. When the chambers are pressurizing, the ground rises. When pressure releases through venting, the ground falls back. The caldera has been measured rising and falling multiple inches over periods of years throughout the monitoring record. In March of 2026, sensors detected a new phase of uplift in a specific section of the caldera. The ground in that region had been slowly falling for several years prior, suggesting a period of depressurization. Then the trend reversed. Something was pushing upward again from below. The science team cross-referenced the uplift location with the new hidden earthquake map. The region showing the most ground rise overlapped with one of the zones that had shown reduced fluid channel activity underground. The venting pathways in that area appeared partly blocked. Pressure was building with fewer routes to escape. The cap was still functioning. The overall system was still venting, but in one section of the caldera, the balance between pressure input and pressure release had shifted. Scientists flagged it for intensified monitoring. And then, a few weeks later, a bright blue pool of boiling water appeared at the surface in an area of the park where nothing like it had ever been recorded. It appeared almost overnight. The ground around it was sterile, stripped of all biological life by the heat. 30 miles beneath your feet, the rock is hot enough to glow. 200 miles down, it is hot enough to flow. And somewhere in that deep structure, a column of unusually hot rock pushes upward toward the surface, feeding everything above it with relentless, continuous heat. Geologists call it a hotspot. The Yellowstone hotspot has been active for roughly 16 million years, as the North American tectonic plate has slowly drifted southwestward over it. The hotspot has burned a chain of ancient calderas across what is now Idaho and Wyoming, a scar trail of past super eruptions stretching nearly 400 miles across the landscape. The current Yellowstone caldera sits at the northeast end of that scar trail, the most recent location where the continental crust has sat directly above the hotspot's peak heat output. As the plate continues its slow movement, the hotspot will eventually move to a new position beneath Montana, though on a timescale of millions of years. At the base of the system, the mantle plume brings material up from deep in the mantle, rock that is hotter than the surrounding mantle by several hundred degrees Fahrenheit. As this hot material rises and the pressure above it decreases, portions of it begin to melt, forming new basalt magma that feeds into the deep chamber 12 to 31 miles underground. The thermal output from this plume is enormous. Scientists have calculated that the heat flowing out of the Yellowstone system exceeds the output of every nuclear power plant currently operating in the United States combined, and it releases that heat continuously, every single day, year after year. The ground temperature in some areas of the park is warm enough near the surface to cook food a few feet underground. For decades, the standard model of this system described the mantle plume as a roughly vertical column, rising straight up beneath Yellowstone like a blowtorch aimed directly at the underside of the crust. The heat pathway was simple. Deep hot rock rises, magma forms. Magma feeds the chambers above. The chambers power the surface features. That model was clean, logical, and, as it turned out, incomplete. Scientists studying the wider tectonic context of the region noticed something that the simple vertical plume model could not explain. The magma reservoirs beneath Yellowstone were not centered directly over the hotspot's expected deep root. They were offset. The chambers pooled toward the east, while the tectonic plate was moving to the southwest. If the plume rose straight up, the chambers above it should shift in the direction of plate movement, trailing westward over time. They did the opposite. Something was tilting the pathway. Something was directing the heat in a way that the standard model did not account for. And in April of 2026, a research team published the answer. The mantle plume beneath Yellowstone was not straight. It was tilted, kinked, and connected to a much broader tectonic structure than anyone had described before. The implications of that finding changed the map of the entire western United States. In April of 2026, a research team published a geological study that contradicted a model that had stood largely unchallenged for decades. The paper described the pathway connecting the Yellowstone magma system to its deep mantle source, and it looked nothing like the simple vertical pipe that textbooks had illustrated. The team used an imaging technique called seismic tomography, the same basic approach that a medical scanner uses to build a three-dimensional image of the inside of the human body. Instead of using X-rays, seismic tomography uses earthquake waves. When a seismic wave passes through hot, partially molten rock, it slows down. When it passes through cold, solid rock, it moves faster. By recording how long waves take to travel between thousands of sensors, scientists can reconstruct the internal structure of the crust and upper mantle in extraordinary detail. The picture that emerged from this study showed the Yellowstone plume tilting sharply. Instead of rising straight upward, the hot rock column beneath Yellowstone angled toward the southwest at depth, before bending back upward toward the surface. The pathway was not a vertical pipe, it was kinked. This tilting connected Yellowstone to a much broader system of underground magma movement that spread across the entire Basin and Range province, the vast geologically active region covering much of Nevada, Utah, and the American Southwest. The Yellowstone hotspot was not an isolated feature. It was part of a network, connected underground to tectonic forces operating across hundreds of miles of the western United States. The discovery had immediate implications for how scientists modelled the pressure supply to the Yellowstone chambers. A straight vertical plume fed the system from directly below at a predictable rate determined mainly by the plume's own temperature and rise speed. A tilted, networked pathway introduced additional variables. The rate of magma supply to the deep chamber could be influenced by tectonic stresses occurring far away from Yellowstone itself. An event hundreds of miles to the southwest, a major fault movement or a shift in plate dynamics, could theoretically affect how quickly material moved through the tilted pathway and into the deep chamber below Yellowstone. The paper also raised a separate question that the team acknowledged they could not yet answer. If the plume tilts toward the southwest at depth, why do the magma reservoirs pool toward the east at shallow depths? The two observations seem to point in opposite directions. The deep pathway heads southwest. The shallow chambers accumulate northeast. Something in the middle of the system is redirecting the material, and scientists do not currently understand the mechanism responsible. That gap in understanding matters because the answer to that question would clarify how the system responds to changes in the deep feed rate. If the redirecting mechanism is passive, driven purely by the structure of the overlying crust, then changes in deep supply take time to register at the surface. If the mechanism is more dynamic, driven by the active pressure within the system, changes at depth could propagate upward faster than current models predict. Scientists studying the data from 2026 knew they were working with an incomplete picture. Every new discovery revealed a system more complex, more interconnected, and more capable of surprising them than the previous model had suggested, and the complexity had only been growing. To understand what the tilted magma pathway actually looks like, picture a highway system seen from directly above. You expect it to run in straight lines from city to city. Then someone shows you a map and the road bends, curves back on itself, and connects to a completely different road system 2 states away, before looping back to where you expected it to go. That is essentially what scientists found when they traced the deep pathway feeding the Yellowstone system. The tilted pathway angles toward the southwest as it descends into the deep mantle, then redirects upward toward the surface. Along that tilted section, the hot rock does not travel alone. It moves through an underground region that connects to the broader tectonic environment of the western United States, a zone called the Basin and Range Province. The Basin and Range is a vast area covering much of Nevada, Utah, southern Idaho, and parts of Arizona and New Mexico. Geologically, it is one of the most stretched and fractured pieces of continental crust on Earth. The crust there has been pulled apart over millions of years, thinning it and creating a landscape of parallel mountain ranges separated by flat valleys. Beneath that thin, stretched crust, the mantle sits unusually close to the surface. The tilted Yellowstone pathway passes through the edge of this stretched zone. The thin crust and the elevated mantle temperature in the basin and range create conditions where magma moves more freely, where heat conducts more efficiently, and where the pathway connecting deep mantle material to the surface encounters less resistance than it would beneath thicker, colder continental crust. What this means practically is that the Yellowstone system is not a self-contained engine running in isolation. It is the northeastern end of a broader thermal and tectonic network. The amount of heat and magma feeding into Yellowstone from below is influenced by conditions spread across a region spanning hundreds of miles. Before this discovery, scientists modelled the Yellowstone system as having a relatively predictable and stable deep supply. The plume rose, it fed the chambers fed the surface. The rate of supply changed slowly over geological time. Events far away from Yellowstone were not considered significant inputs to the system's behaviour on shorter timescales. After this discovery, that assumption requires revisiting. Major seismic events or tectonic shifts in the basin and range could, in principle, affect flow rates through the tilted pathway. The degree of that influence and the timescales involved remained unclear from the published data, but the connection itself was no longer theoretical. The pathway had been mapped. The team that published the paper acknowledged they were mapping a system whose full implications would take years to work through. The data showed the connection. The models to explain how that connection affects surface level risk were still being developed. Meanwhile, ground deformation data, the hidden earthquake map, and the gas emission readings at the surface were all feeding into Yellowstone's monitoring network. And in early 2026, that network had started registering something it had not seen in that specific combination before. The ground was rising in a zone of low fluid activity. A new hot spring had appeared, and sensors were recording subtle changes in the emission chemistry of the gases escaping through the cap. Here is the mystery that has divided volcanologists since the 2026 tilted plume discovery. The deep pathway descends to the southwest. Everything about the geometry of that tilt should push magma accumulation in the same direction. Material moving up and to the northeast from a southwest dipping source should deposit somewhere in the middle, or possibly toward the northwest, depending on how the overlying crust channels it. Instead, the magma reservoirs consistently pool to the east and northeast of where the deep source sits. The shallow chamber and deep chamber both sit offset eastward from the plume's deep root. The asymmetry is consistent and significant. This is measurable enough that multiple independent research teams have confirmed the pattern. Everyone agrees it exists, nobody agrees on why. One hypothesis points to the structure of the crust itself. The crust beneath Yellowstone is not uniform. It is thinner to the west and slightly thicker to the east, a result of how the basin and range extension process has stretched the western portion more aggressively. Thicker crust on the east side may create a natural barrier that slows magma movement in that direction, causing it to pool along that boundary the way water pools at the edge of a tilted surface. A second hypothesis involves the movement of the North American plate. The plate moves toward the southwest at about 1 inch per year. As it does, the crust at depth is being dragged in that direction relative to the fixed hotspot below. Some researchers argue that this drag creates a zone of slightly lower pressure to the east of the hotspot's surface position, and that magma, always moving toward lower pressure, preferentially accumulates in that lower pressure zone. A third hypothesis, more speculative, suggests that the basin and range tectonic forces are actively pulling magma westward at depth, while the pressure dynamics of the Yellowstone chambers themselves push material eastward at shallower levels, creating a tug-of-war that results in the observed eastward pooling as a kind of equilibrium position. None of these three explanations is fully satisfying. Each requires assumptions about underground conditions that are difficult to verify directly. The data that would distinguish between them requires either deeper imaging than current technology can cleanly achieve, or a longer observational record of how the magma distribution shifts over time. The practical importance of solving this mystery goes beyond academic curiosity. The location where magma pools determines which part of the surface sits most directly above the highest pressure zone. The eastern pooling pattern means that the sections of the caldera on the east side receive the most direct pressure input from below. Ground deformation in those regions should be watched most closely if conditions change. In March of 2026, the ground uplift that sensors detected occurred on the eastern side of the caldera. The overlap between the unexplained eastward pooling pattern and the new pressure signal was hard to ignore. Scientists flagged the correlation in their monitoring reports. They were careful to note that ground uplift on its own is a common and expected feature of a living volcanic system. Yellowstone has been rising and falling for decades, but the combination of eastward pooling, reduced venting channel activity in that region, new uplift, and the appearance of a brand new thermal feature at the surface placed that section of the caldera at the top of the monitoring priority list. Something was shifting in the plumbing. The question was what and how far it might go. 630,000 years ago, there were no humans in North America. The continent looked entirely different. Mammoths roamed across grasslands that stretched from coast to coast. giant ground sloths the size of elephants moved through forests in what is now the western United States. The landscape was ancient, quiet by our standards, and on a specific day, it ended violently for a vast portion of the continent. The Yellowstone hotspot erupted. The eruption did not look like a typical volcano. There was no single cone, no lava fountain shooting skyward from a mountain peak. The entire caldera, a depression roughly 34 miles wide and 45 miles long, fractured along its edges and collapsed. The roof of the magma chamber above the main reservoir broke apart and fell inward as millions of cubic miles of magma forced its way to the surface through a ring of fractures around the caldera's perimeter. The volume of material ejected dwarfed any eruption in recorded human history. The ash cloud that rose from the event reached into the upper atmosphere and began spreading. Within days, ash fell across the entire western half of North America. Eventually, a thick layer of volcanic ash, in some places several feet deep, covered territory stretching from the Pacific coast to the Mississippi River. The ash layer from this eruption, called the Lava Creek Tuff, is identifiable in geological deposits across 23 states. The sky over North America went dark. Sunlight scattered and dimmed as ash particles filled the upper atmosphere. Temperatures dropped. Plant growth slowed. The ecosystems across the continent were disrupted on a scale that dwarfed any ordinary natural disaster. The effects persisted for years. For the megafauna living in the region, the immediate consequences were catastrophic. Animals within hundreds of miles of the eruption site were buried, burned, or suffocated by the ash and pyroclastic flows, superheated clouds of gas and rock fragments moving outward from the caldera at speeds exceeding 100 miles per hour. Species that survived the initial eruption faced starvation as vegetation collapsed under ash deposits too thick for recovery. The eruption shaped the landscape in ways still visible today. The caldera itself, the giant sunken depression that gives Yellowstone its distinctive geology, was carved by that eruption. The lake that fills part of it, Yellowstone Lake, sits in the collapsed floor of the chamber that partially evacuated 630,000 years ago. The thermal features scattered across the park draw their heat from the same system that produced that event. The Lava Creek eruption was the third major supereruption in the Yellowstone hotspot's history at its current location. The first occurred 2.1 million years ago. The second occurred 1.3 million years ago. The spacing between these events suggests an approximate recurrence interval, though volcanologists are quick to point out that volcanic systems do not operate on fixed schedules. The intervals between eruptions at Yellowstone have varied significantly, and the hotspot may be weakening over geological time as the continental crust thickens and resistance increases. What the pattern does confirm is that this system is capable of producing an event unlike anything modern civilization has ever experienced, and the new maps of what sits below, the deep chamber, the tilted pathway, the breathing cap, all describe a system that retains the fuel supply for another event of that scale. Whether or when is unknown. What happens if it does is the question that terrifies every scientist who has spent a career studying the data. 2.1 million years ago, 1.3 million years ago, 630,000 years ago, 3 super eruptions, 3 catastrophic events separated by intervals of roughly 800,000 years, then roughly 670,000 years, and right now 630,000 years after the last one. That sequence gets attention quickly. If someone tells you a catastrophic event has happened 3 times, with roughly equal gaps between them, and you are currently sitting at the far end of the most recent gap, the obvious question forces itself forward. Volcanologists have a careful answer. They are clear that Yellowstone does not operate on a fixed clock. The gaps between the 3 known super eruptions were not equal. The first interval was longer, the second was shorter. The system responds to geological conditions, not a timer. and current monitoring data shows no sign of the specific internal conditions required to trigger an eruption. But the 3 eruption record reveals something important beyond timing. Each event erupted from the same basic location, the caldera that forms the centre of what is now the park. Each eruption left a distinct geological signature in the rock record, a layer of ash and welded tuff identifiable across North America, and, in diluted form, in ocean sediment cores from across the Pacific. Each eruption produced roughly comparable volumes of material. The system appears to have been recharging toward a similar energy state each time. The first super eruption, called the Huckleberry Ridge event, produced the largest volume of the 3. The thick ash deposits from that eruption cover territory, stretching from Nebraska to California, and the deposits in some locations in Idaho still measure dozens of feet thick. That event was powerful enough to have global climate implications, cooling temperatures across the northern hemisphere for years. The second eruption, the Mesa Falls event, was smaller but still enormous by any ordinary measure. It reshaped a section of what is now eastern Idaho and deposited ash across a wide swath of the western United States. Then the Lava Creek eruption formed the current caldera 630,000 years ago. Between these 3 major events, smaller eruptions occurred. Lava flows have covered sections of the caldera floor relatively recently in geological terms, with some flows dating to only 70,000 years ago. The system produces eruptions of varying sizes. The super eruptions represent extreme events at the high end of a range that also includes smaller, more localized volcanic activity. The pattern of 3 super eruptions followed by extended quiet is consistent with how scientists understand the recharge process. After a super eruption empties a significant fraction of the magma chambers, the system requires a vast amount of time to rebuild the pressure and melt fraction necessary to trigger another comparable event. That recharge happens slowly, fed by continuous heat from the mantle plume below. Whether the system is currently in a recharge phase heading toward another super eruption, or whether it is gradually declining as the hotspot weakens, remains one of the central unresolved questions in Yellowstone science. The evidence points in both directions, and distinguishing between a charging system and a declining one from current data alone is genuinely difficult. What is not difficult to assess is what the outcome of a fully charged eruption would look like. That part of the calculation has a clear answer, and the scale of it forces every researcher who works on Yellowstone to sit with the data for a while before moving on. Hour 0. The caldera fractures. The roof of the shallow magma chamber, the lid that has held for 630,000 years, loses structural integrity along the fault lines that ring the depression. It happens across the entire perimeter simultaneously, not at a single point. The ground along the caldera edge drops inward as the chamber below partially evacuates, and the material inside, partially molten rhyolite under enormous pressure, forces its way toward the surface through every fracture that opens. In the first minutes, pyroclastic flows spread outward from the caldera rim. These are dense, superheated avalanches of gas, ash, and rock fragments, moving faster than a commercial jet at low altitude. Temperatures inside a pyroclastic flow exceed 1,000 degrees Fahrenheit. Everything within roughly 100 miles of the caldera is destroyed or buried within the first hour. The cities of Jackson, Wyoming, and Idaho Falls, Idaho sit well inside that range. The eruption column rises into the atmosphere at extreme speed. Within the first hour, ash and gas reach the stratosphere, the layer of atmosphere above most weather. Once there, wind patterns spread the material across the continent. Ash begins falling across the western United States within the first few hours of the eruption. By hour 6, ash accumulations become measurable in cities like Salt Lake City, Utah, roughly 300 miles away. An inch of ash sounds minor. It is heavy enough to collapse roofs, clog all combustion engines, contaminate every open water supply, and render all exposed agricultural land unusable until the ash is cleared or dissolves. Emergency response vehicles stop working. aircraft cannot fly anywhere in the ash zone. By hour 24, the ash cloud has spread across much of the continental United States. Measurable deposits reach the East Coast within days. The thickest zone, the region receiving more than a foot of ash, covers most of the Great Plains, the breadbasket region that produces a significant fraction of North America's grain supply. Crops across that zone are destroyed instantly. Power grids across the western United States fail as ash shorts out transformers and clogs cooling systems at power plants. Communication networks built on physical infrastructure in the ash zone go dark. The logistical systems that move food, fuel and medicine across the country are disrupted simultaneously. At hour 48, the stratospheric ash layer begins reflecting sunlight back into space. Global average temperatures start dropping. The agricultural disruption from the ash on the ground is compounded by reduced sunlight reaching crops in regions far outside the direct ashfall zone. Growing seasons shorten globally. Food supply chains that depend on North American grain exports begin to feel the pressure. None of this is prediction or extrapolation from theory. This is what geological records from smaller eruptions, combined with atmospheric modelling and the known volume of the Yellowstone chambers, produces when the numbers are worked through carefully. The record of past eruptions confirms the scale. The atmospheric models confirm the spread. The current monitoring data shows no indication of an imminent eruption. The melt fraction in the shallow chamber remains low. The cap is venting. The system is stable by the measures available. But the new maps of the deep chamber, the tilted pathway, the hidden earthquake network, and the pressure signals in the eastern caldera all describe a system far more complex than the instruments were originally designed to monitor. Scientists watching those instruments in 2026 knew they were tracking something bigger and stranger than the old models had described. And the questions they could not yet answer were the ones that mattered most. The ash stops falling eventually. The eruption column weakens over days and weeks as the pressure inside the emptied chambers drops. The visible drama at the caldera slows, and then the slower, quieter disaster begins. The one that reaches every person on Earth, including those who never heard the eruption and never saw a single flake of ash. Volcanic winter. When a massive eruption pushes material into the stratosphere, the finest particles, sulfur dioxide gas and microscopic ash, stay suspended at altitude for months to years. Unlike weather at ground level, the stratosphere has no rain to wash particles out. The material circulates with high-altitude wind patterns, spreading into a thin global veil that reduces the amount of sunlight reaching the surface. A Yellowstone super-eruption would inject more material into the stratosphere than any eruption in human history. Scientists estimate the resulting temperature drop at the surface could average somewhere between 3 and 7 degrees Fahrenheit globally. That range sounds small. It is devastating in practice. 3 degrees of average cooling does not mean slightly chilly winters. It means the growing season in the Northern Hemisphere shortens by weeks. It means late frosts kill crops that would otherwise survive. It means precipitation patterns shift as atmospheric circulation changes. The regions that historically grow the food that feeds billions of people become unreliable producers simultaneously. History provides a smaller scale preview. In 1815, the eruption of Mount Tambora in Indonesia pushed enough material into the stratosphere to drop global temperatures by about 3 degrees Fahrenheit. The following year, 1816, became known as the Year Without a Summer. Crops failed across Europe and North America. Famine spread across multiple continents. Food prices spiked. Social instability followed. Tambora released roughly 1/40th of the material that a full Yellowstone super-eruption would produce. Scale that up 40 times, and the agricultural disruption extends from a single bad growing season to a multi-year collapse of food production in the most critical farming regions on Earth. Supply chains built to handle ordinary disruptions carry no buffer for a simultaneous failure of major grain-producing regions across multiple continents. The world currently stores roughly 90 days of global grain reserves. A volcanic winter reducing harvests by 30 to 40% for 2 to 3 consecutive years would exhaust those reserves well before recovery was possible. The effects cascade in ways that are difficult to fully trace. Reduced food supply drives prices up, which hits the poorest populations hardest and fastest. Resource competition intensifies. Governments facing simultaneous infrastructure loss and food insecurity strain under pressures they were not designed to manage concurrently. None of this requires the eruption to be the end of human civilization. Humans survived the Toba eruption roughly 74,000 years ago, an event potentially larger than any Yellowstone eruption, though the human population at that time was far smaller and the interconnected global systems that would now be at risk did not exist. The scale of the current threat is different because the scale of current vulnerability is different. Modern civilization is highly optimized and highly interconnected. Efficiency in food production and distribution reduces buffer capacity. A disruption large enough to overwhelm the buffer has no precedent in the era of organized global society. Scientists who study this scenario are careful to separate what the data shows from extrapolation. The data shows a system capable of producing an event of this scale. The monitoring data shows a system currently stable. Both things are true simultaneously, and the gap between stable and unstable is measured in processes happening miles underground, some of which the instruments above were only recently redesigned to detect. In early 2026, a ranger conducting a routine walk through the Norris Geyser Basin in Yellowstone noticed something that had not been there before. A pool of water, vivid blue and perfectly clear, was filling a depression in the ground where dry, cracked earth had existed during previous inspections. The water was boiling. The ground immediately surrounding it was bleached white and completely sterile, stripped of every microorganism by the extreme heat and acidity of the fluid. Scientists were notified. A team arrived within days. The pool was measured at temperatures exceeding 250 degrees Fahrenheit at the surface, boiling well above normal water temperature due to the mineral content raising the boiling point. At depth, the temperatures would be significantly higher. The water chemistry showed extremely high concentrations of chloride and silica, signatures of deeply circulating hydrothermal fluid that had travelled long distances through rock before reaching the surface. The sudden appearance of a new thermal feature at the surface is not unprecedented at Yellowstone. The Norris Geyser Basin in particular has a documented history of rapid hydrothermal changes. The basin sits above one of the most geologically active sections of the entire park, directly over a zone where multiple fault systems intersect and where hydrothermal fluid movement is especially intense. But the timing of this specific appearance was significant. It occurred weeks after the ground uplift sensors detected a pressure shift in the eastern caldera. And when scientists overlaid the location of the new pool onto the hidden earthquake map generated by the artificial intelligence analysis, the pool sat at the surface endpoint of one of the denser fluid channel clusters identified in the subsurface data. A new thermal feature appearing at a location where the underground data showed active fluid movement was consistent with one explanation. A previously blocked or dormant channel had opened. The pressure building in the subsurface had found or forced a new escape route to the surface, and the superheated hydrothermal fluid now flowing through that route was pooling where the channel met the surface. In the context of the cap's breathing mechanism, this was the system creating a new vent. The old venting pathways in the region had partly clogged. The pressure had risen enough to fracture a new pathway through the rock above. The blue pool was the visible result of that fracture, a new exhalation point for a system that needed to release pressure and found a way to do it. For scientists, the blue pool carried two messages simultaneously. The first was reassuring. The system was still venting. Pressure was still finding escape routes. The cap was still functioning, even if through newly formed channels. The second message was less comfortable. The system had been under enough pressure in that region to fracture new rock and open new pathways. That requires a pressure differential significant enough to overcome the mechanical strength of the fractured crust above. The pool attracted significant public attention. Tourists photographed it. News outlets covered it. Scientists explained it in terms of routine hydrothermal dynamics, while privately noting that the combination of factors producing it, the ground uplift, the blocked channels, the new fracture pathway, formed a pattern worth watching extremely carefully. 2026 had now produced 3 overlapping signals in the same region of the caldera, and none of them had a fully satisfying explanation yet. The blue pool was beautiful and terrifying in equal measure, but its surface appearance was less informative than what its chemistry revealed once the laboratory analysis came back. The fluid filling the pool carried a specific chemical fingerprint. The ratio of chloride to sulfate in the water, combined with the concentration of dissolved silica, told scientists something precise about where that water had been before it reached the surface. High chloride with low sulfate is a signature of deeply circulating water that has travelled through hot rock at significant depth without extensive interaction with oxygenated shallow groundwater. The chemistry in the new pool matched that profile clearly. This meant the water in the pool had not percolated down from recent rainfall and been heated in the shallow rock near the surface. It had circulated through the deep hydrothermal system, travelled through rock at temperatures consistent with proximity to the cap layer or the upper margin of the shallow magma chamber, and then risen to the surface through the newly opened channel. That depth signature confirmed something important. The new vent was connected to the main hydrothermal system, not a superficial local anomaly. The fluid was coming from the same deep reservoir that feeds all the major thermal features in the region. The new pool was a new window into the same underground system that had been shifting since the pressure changes in March. The silica concentration added another layer. High dissolved silica in hydrothermal fluid means the water has been in contact with silicate-rich rock at elevated temperatures for an extended period. The silica in the pool matched concentrations typically associated with temperatures between 450 and 550 degrees Fahrenheit at the point of origin underground. That temperature range is consistent with conditions near the top of the magma cap, the zone where supercritical water transitions back to a regular hydrothermal fluid as pressure decreases during ascent. Scientists built a model of what likely happened underground to produce the new spring. The pressure buildup in the eastern caldera region had forced hydrothermal fluid upward through the existing fractured rock. As the fluid moved upward and cooled, silica crystallized out of solution and slowly narrowed the channels it was moving through. When enough channels narrowed and the pressure had no easy route to the surface, the overpressurized fluid found the weakest point in the rock above and fractured it. A new crack opened. The fluid rushed upward through it and pooled at the surface. The process was exactly what the breathing model predicted would happen locally when venting channels became partly obstructed. A new pathway opened to compensate. The system was self-regulating within limits. The word within limits carried significant weight. The self-regulation works as long as the pressure input from below does not exceed the rate at which new venting pathways can open. Each new pathway requires fracturing rock, which requires a minimum pressure threshold. If pressure builds faster than new fractures can form, the gap between pressure input and pressure output widens. The system moves toward a state where the cap is holding more than it releases. Scientists watching the data in 2026 had no evidence the system was approaching that threshold, but they were watching a system that had just created a new major surface feature and had registered overlapping pressure signals in the same region within the same month. The pattern was new. The models for interpreting it were still being developed. The sensors are buried in the ground across Yellowstone in dozens of locations. They are precise enough to detect vertical ground movement of a fraction of an inch over a period of weeks. They run continuously, and in March of 2026, several of them in the eastern portion of the caldera began registering a slow, persistent upward trend. Ground uplift at Yellowstone is not unusual. the caldera has been measured rising and falling throughout the history of instrumented monitoring. In the 1970s and 80s, the ground in parts of the park rose by nearly 3 feet over roughly a decade before reversing and subsiding again. Researchers at the time documented the movement carefully, but interpreted it as a normal expression of a living volcanic system, fluid and magma shifting below the surface without any eruption-scale pressure building. The key question with any new uplift event is always the same. Is the ground rising because magma is pushing upward, implying an increase in the melt fraction and a rise in eruption-relevant pressure? Or is it rising because hydrothermal fluid, water and gas at high pressure is migrating into a new underground region and inflating the rock there without any increase in actual magma volume? The distinction matters enormously. Magmatic uplift, driven by actual molten rock moving toward the surface, is a much more serious signal than hydrothermal uplift, driven by fluid redistribution. Both produce rising ground. The data required to tell them apart includes the chemistry of gas emissions at the surface, the seismic signature of any accompanying micro-earthquakes, and the spatial pattern of the uplift itself. In the March 2026 event, the initial analysis pointed toward a hydrothermal origin. The uplift was concentrated in a relatively small area, rather than spread across the entire caldera floor, which is more typical of magmatic inflation. The gas emissions at nearby vents did not show the sharp increase in sulfur dioxide that typically accompanies magma moving closer to the surface, and the hidden earthquake data for the uplift zone showed activity patterns consistent with fluid movement through existing fracture networks rather than new fractures being forced open by pressurized magma. That assessment was cautiously reassuring. Hydrothermal uplift means pressurized water and gas are redistributing underground. The system is active, but the primary driver is fluid, not fresh magma. But the overlap of signals in one region, the uplift, the reduced venting channel activity, the new surface spring, and the positioning in the zone of unexplained eastward magma pooling, made the interpretation more complicated than any single signal would be on its own. The monitoring team issued an advisory to continue elevated observation of the eastern caldera region. Yellowstone has a monitoring system that is among the most comprehensive of any volcanic system in the world. Dozens of seismometers, multiple continuous GPS stations measuring ground position to millimeter accuracy, gas sensors, temperature sensors in thermal features, tilt meters measuring subtle changes in the angle of the ground surface. All of that data feeds into a joint monitoring program run by the United States Geological Survey and the University of Utah. The people watching that data in 2026 were not panicking, but they were paying very close attention to one specific corner of the caldera where 3 independent signals had converged on the same location within the span of a single month. Shake a bottle of soda. The carbonation, carbon dioxide dissolved under pressure into the liquid, wants to escape. The moment you release the cap and the pressure drops, bubbles form instantly throughout the liquid and race toward the surface. The process is fast, dramatic, and hard to stop once it starts. Miles underground at Yellowstone, a slower version of that same process runs continuously. Carbon dioxide dissolved in the magma below remains in solution as long as the pressure surrounding it stays high. As magma slowly rises toward lower pressure zones, the carbon dioxide begins to separate out. Bubbles form. They rise through the magma faster than the melt itself moves, because gas is far lighter than molten rock. Those bubbles reach the base of the magma cap and enter it. Some of the carbon dioxide dissolves back into the supercritical water there. Some continues upward as bubbles, squeezing through fractures and porous zones in the rock above the cap. Through hundreds of feet of fractured crust, the gas molecules work their way upward, finding the path of least resistance through the rock structure. At the surface they emerge through soil, through hot spring pools, through the floor of the lake sitting in the caldera. Scientists measure carbon dioxide output from the Yellowstone system and track it as one of the key indicators of what is happening underground. The park releases between 45,000 and 60,000 tons of carbon dioxide per day through this natural process, every day without stopping. That number provides a baseline. When the daily output rises significantly above that range, it suggests more gas is escaping from the magma below, which can mean the magma is rising slightly or becoming less pressurized. When output drops, it can mean either that magma activity is decreasing or that the escape pathways are narrowing. The pathway the gas takes through the rock leaves a chemical signature in the materials it passes through. As carbon dioxide moves upward through rock containing calcium-rich minerals, it reacts with those minerals and slowly dissolves them, widening channels over time. This acid dissolution is one of the mechanisms that maintains the permeability of the rock above the cap, keeping pathways open for continued venting. But the same process can also weaken the structural integrity of the rock. Dissolved minerals leave behind voids. The rock above the cap, already fractured and stressed by decades of thermal expansion and contraction, becomes progressively more porous as acid dissolution continues. In most areas, this is fine. The rock remains structurally competent despite the porosity. In localized zones where dissolution has been most intense, the rock above certain channels has become significantly weaker than the surrounding material. The new fracture pathway that produced the Blue Pool in 2026 opened into exactly one of those weakened zones. The acid dissolution had been working on the rock there for an extended period, reducing its resistance to fracture below the threshold required to hold against the pressure buildup. This creates a feedback loop worth tracking. The more the system vents, the more acid dissolution occurs, the weaker certain zones become, the more likely those zones are to fracture under future pressure increases. The venting pathways that keep the system stable are also gradually modifying the structure of the rock they flow through. Over geological time, this process reshapes the entire upper crust of the caldera. Over human timescales, it means the specific locations where new fracture pathways open during pressure events are partially predictable based on where dissolution has been most concentrated. Scientists mapping the underground chemistry are building that predictive picture. It was not complete in 2026. Every system has a threshold, a point where the balance tips. For Yellowstone's breathing mechanism, that threshold is the moment the venting pathways close, faster than the system can open new ones. Pressure accumulates in the cap. The gas that was escaping stays trapped. The supercritical fluid that was flowing upward pools below the blockage, and the pressure meter, if you could read it underground, begins climbing. Scientists refer to the specific scenario where this tipping point is reached as the critical clogging scenario. It is not inevitable. The system has been venting continuously for tens of thousands of years without triggering it. The cap has experienced partial blockages before, as the evidence from various periods of caldera uplift in the monitoring record suggests, and each time the pressure found new pathways and the venting resumed. But each partial blockage leaves behind a geological record of what happened. Layers of silica deposits in the rock above the cap, hydrothermal breccia, fragmented rock that was broken apart when a pathway forced itself open under pressure, chemical alteration zones where supercritical fluids reacted with the surrounding rock. These layers tell scientists how many times the system has gone through partial blockage and recovery cycles, and how intense those cycles were. The record shows a system that has experienced repeated cycles of pressure build-up and release over its history. Each cycle left a different fingerprint depending on how much pressure accumulated before a new vent opened. In some cycles, the pressure released gently through a widening of existing fractures. In others, the opening of new pathways was more violent, leaving behind shattered rock and hydrothermal explosion craters at the surface. Hydrothermal explosion craters already exist at Yellowstone, including several large ones visible as lake features. These are not volcanic eruptions, they are steam explosions, events where superheated water trapped below an impermeable surface layer suddenly flashes to steam when the pressure exceeds the rock's containment strength. The explosion fragments the rock above and blasts it outward, leaving a crater. These events can occur with very little warning. The largest known hydrothermal explosion at Yellowstone produced a crater roughly 5 miles wide. A hydrothermal explosion is orders of magnitude smaller than a magmatic supereruption, but it is also far more likely on any given human timescale, and it would occur with minimal warning, even with the current monitoring network, because the pressure buildup driving it happens in a localized zone over a relatively short period. The critical clogging scenario that leads to a full magmatic eruption requires a different set of conditions. The melt fraction in the shallow chamber needs to be substantially higher than it currently sits. The deep chamber needs to have been supplying heat and volatiles at an elevated rate for a sustained period. The cap needs to have lost most of its venting capacity, and the rock above the cap needs to have weakened enough that the pressurized magma below can fracture it. Current data does not show that combination present. The melt fraction is low, the deep supply rate appears stable, the cap is functioning. But the sequence of events in early 2026 offered a preview of what partial clogging and its consequences look like in real time. A small version of the process that scaled up would become the most destructive natural event in the modern era. The monitoring team watching the Eastern Caldera in 2026 was watching exactly that preview unfold, signal by signal, in the data. The problem with predicting a volcanic eruption is that the most important processes happen miles underground, invisible to direct observation, accessible only through instruments measuring secondary effects at the surface. Every reading is indirect. Every model involves assumptions about conditions that cannot be measured precisely. Scientists have 3 primary tools for monitoring Yellowstone: seismology, geodesy, and geochemistry. Each measures a different aspect of the system. Together, they build a picture of what is happening below. Seismology measures earthquake activity. The location, depth, size, and frequency of quakes beneath the park tell scientists where rock is fracturing, where fluid is moving, and whether new fractures are forming in areas that were previously quiet. A sudden increase in earthquake swarm activity at shallow depths near the caldera center, especially if the quakes become progressively shallower over days, is one of the signals that would prompt an escalation in alert level. Geodesy measures ground deformation. The network of global positioning system receivers planted across the park tracks ground position continuously. Rising ground in the caldera suggests increasing pressure below. The rate of rise, the spatial pattern, and whether the rise is accelerating or steady all inform how scientists interpret what is driving it. A caldera uplift rate of more than a few inches per year, combined with other escalating signals, would push the alert system toward higher readiness. Geochemistry measures the gases escaping at the surface. Ratios of sulfur dioxide to carbon dioxide in emissions change when the magma itself is moving. Fresh magma carries more sulfur dioxide in its dissolved volatiles. When sulfur dioxide emissions spike sharply at the surface, it indicates magma rising closer to the surface and releasing its gases. This is one of the more direct signals available to surface monitoring, because the chemistry of the gas reflects the chemistry of the source. In 2026, none of these 3 systems were showing the combination of signals that would move Yellowstone's alert level upward. The earthquake swarms occurring were consistent with ordinary hydrothermal activity. The ground uplift was localized and modest. The gas chemistry at surface vents showed no significant sulfur dioxide increase. The monitoring team continued its observation of the Eastern Caldera region with elevated attention but no public alarm. This is itself a feature of how volcanic monitoring works. The threshold for raising a public alert is high, because false alarms carry real costs. Tourism stops, evacuation planning strains resources, economic disruption follows. And a system like Yellowstone, which shows ongoing activity as its normal state, requires distinguishing genuine escalation from ordinary background noise. The challenge scientists acknowledged openly in 2026 was that the models used to set alert thresholds were built on data collected before the discovery of the deep chamber, before the hidden earthquake map revealed the full extent of the underground plumbing, and before the tilted pathway paper changed the understanding of how the deep supply reaches the chambers. The old thresholds were calibrated to an incomplete picture. Building new, better calibrated thresholds would take years of additional data collection and modelling. In the meantime, the monitoring continued using the best tools available, watching a system that kept revealing it was larger and stranger than any previous model had fully captured. Numbers about underground heat can feel abstract. Miles of depth, millions of years, tons of carbon dioxide per day. The scale overwhelms the imagination. So here is a comparison that lands differently. Every nuclear power plant currently operating in the United States generates heat to produce electricity. The United States operates roughly 93 nuclear reactors across the country. Together, they produce an enormous amount of thermal energy, enough to power tens of millions of homes continuously. Yellowstone releases more heat through its natural venting process every single day than all of those reactors combined. Every day, without a turbine, without a fuel rod, without any human infrastructure. Just rock, water, and the heat of a mantle plume that has been burning for 16 million years. The heat flow from the Yellowstone caldera measures roughly 30 watts per square metre across the surface of the thermal basin. Normal continental crust releases roughly 1/10 of a watt per square metre. Yellowstone runs 300 times hotter than the surrounding region. That differential is what drives every geyser, every hot spring, every fumarole, every mud pot, and every thermophilic microbial mat glowing yellow and orange around the edges of the thermal pools. That heat is also what keeps the magma system from cooling and solidifying. A magma chamber that loses heat faster than it receives it will gradually crystallize. The melt fraction drops. The system becomes sluggish. Eventually it freezes entirely and the volcanic activity ends. This is what happened to the ancient calderas burned by the Yellowstone hotspot across Idaho and Nevada millions of years ago. The plate moved them away from the heat source. They cooled. They died. The current caldera still sits directly above the peak heat output of the hotspot. The system is still receiving more heat than it loses. The melt fraction in the shallow chamber is low but stable, meaning the heat input and the heat loss are roughly in balance. The system is maintaining, not charging aggressively, but sustaining. What the heat output measurements also reveal is the efficiency of the venting mechanism. The cap and the fractured rock above it are moving an extraordinary amount of thermal energy from depth to the surface every day. Hot springs alone carry heat to the surface at rates that, if converted to electricity, could power a mid-sized city. The venting pathways are working constantly, moving heat that would otherwise accumulate in the chambers and raise the melt fraction. Any significant reduction in venting efficiency would allow that daily heat input to accumulate rather than escape. Even a modest decrease in heat outflow, sustained over years, would slowly raise the temperature of the shallow chamber, incrementally increasing the melt fraction. The change would be gradual. It would show up first in ground deformation data, then in gas emissions, then in increasing seismic activity as the chamber walls flexed under growing pressure. The monitoring system is designed to catch exactly that sequence. The instruments are sensitive enough. The question scientists in 2026 were sitting with was whether the models for interpreting the sequence, built on older, less complete data about the system's actual structure, remained reliable enough to give adequate warning time if the sequence began. 2.5 miles down sits the cap. Above it, between the cap and the surface, lies several miles of the most geologically tortured rock in North America. This rock has been stretched, cracked, recrystallized, dissolved, and reformed repeatedly over hundreds of thousands of years of thermal stress. It is fractured at every scale, from microscopic grain boundaries to fault zones spanning miles. Hydrothermal fluids have moved through it for so long that some sections look less like solid rock and more like a rigid sponge, porous with former fluid channels, some open, some sealed with mineral deposits. The condition of this rock matters more than almost any other factor in determining how the system behaves during a pressure increase. If the rock above the cap is highly permeable, meaning fluids can move through it easily in many directions, pressure increases dissipate quickly as gas and hydrothermal fluid find multiple escape routes to the surface. The cap vents efficiently. The system remains stable. If the rock above the cap is poorly permeable in certain zones, because mineral sealing has closed many of the channels, pressure increases concentrate in those zones. The fluid cannot spread laterally or find easy upward routes. It pushes against the weakest local structure until something fractures. The upper rock above Yellowstone's cap is neither uniformly permeable nor uniformly sealed. It is patchy. Highly permeable zones sit adjacent to more sealed zones. The map of where those different zones exist corresponds closely to the map of where active surface features appear and where the ground is featureless. The dense branching network revealed by the hidden earthquake map captures this patchiness in detail. The busiest fluid corridors in the subsurface data correspond to the most permeable pathways in the upper rock. The quieter zones in the data correspond to less permeable sections. What makes the upper rock even more complex is that its permeability is not static. Acid dissolution from rising carbon dioxide slowly opens channels. Silica deposition from cooling hydrothermal fluids slowly seals others. Thermal expansion cracks old mineral deposits and creates new fracture surfaces. Seismic shaking from the continuous background earthquake activity shifts channel geometry. The map of permeable and sealed zones changes slowly but continuously. Scientists trying to model the cap's breathing efficiency need to know the current permeability structure of the rock above it. Getting that information precisely requires either drilling into the rock at multiple points, which is expensive, technically complex and politically sensitive in a national park, or inferring it indirectly from the seismic data, the gas emission patterns, and the surface deformation measurements. The inference approach works well for large-scale patterns but misses local detail. The blue pool that appeared in early 2026 appeared because a local zone of weakened rock, reduced to low fracture resistance by concentrated acid dissolution, failed under the local pressure pulse. That specific zone was not individually flagged in the broad monitoring data before it failed. The data showed elevated activity in the region. It did not identify the precise spot that would fail or the exact timing. That gap between regional pattern and local detail is one of the most honest limitations scientists working with Yellowstone acknowledge. The system is large, the variations are continuous, and perfect prediction of localized events within it remains beyond current capability. Every year, roughly 3 million people visit Yellowstone National Park. They walk the boardwalks above the thermal basins, stand at the railing watching Old Faithful, drive the loop road past the bison herds, and camp in valleys carved by ancient glaciers and lava flows. Yellowstone is one of the most visited national parks in the country, and for most people, the ground beneath them reads as scenery. The Park Service manages that scenery with detailed protocols built around the reality of what sits below. Boardwalks exist above thermal areas because the ground around hot springs is geologically unpredictable. Thin crusts of silica and mineral deposits can form over shallow hydrothermal features, appearing solid but collapsing under weight into scalding water below. People who leave marked trails in thermal areas are not just risking fines. They are walking on rock that may be a few inches thick above water, hot enough to cause severe burns instantly. Several visitors over the park's history have died in thermal features, usually as a result of falling or stepping through thin surface crusts near hot springs. The ground that looks stable at Yellowstone sometimes is not, at the immediate local scale, entirely separate from the larger volcanic risk below. The visitor management challenge connected to deeper volcanic risk is of a completely different scale. Yellowstone sits in a remote region of Wyoming, but it is surrounded by towns, highways, and regional infrastructure that would all be affected by any significant escalation in volcanic activity. Jackson Hole and the surrounding communities south of the park depend heavily on the park's tourism economy. Idaho Falls to the west, Cody to the east, and Billings, Montana to the north all sit within the broader regional zone that emergency planners have modelled for various levels of volcanic activity. Emergency planning for a significant volcanic event at Yellowstone exists. The United States Geological Survey, in coordination with state and federal emergency management agencies, has produced hazard assessments and response frameworks. These plans cover scenarios ranging from localized hydrothermal explosions, which could occur with little warning and affect a limited area within the park, to large lava flow events, which would be preceded by significant seismic and deformation warning, but would be slow enough for organized evacuation, to the full super eruption scenario, which is assessed as extremely unlikely on any near-term human timescale. The super eruption emergency framework essentially acknowledges that a full-scale event would overwhelm any regional response and require national and international coordination on a scale without modern precedent. The evacuation modelling for a full eruption scenario is complicated by the ashfall zone covering much of the transportation infrastructure that would be needed for evacuation. For the 3 million annual visitors and the permanent residents of the surrounding region, daily life proceeds without active concern about the volcano. The monitoring data reassures scientists. Scientists communicate that reassurance publicly. The gap between what scientists understand about the system's complexity and what the public understands about its true scale is significant, and it is a gap that the new discoveries of 2025 and 2026 widened further. 60 miles southeast of Old Faithful, a seismometer buried in the ground registers a vibration at 3:47 in the morning. The vibration lasts half a second. The magnitude is too small to feel, too small for any person within miles to notice. The instrument records it automatically. The data transmits to a server in Salt Lake City within seconds. By the time the sun rises over the park, that micro-earthquake has been added to the daily log alongside several dozen others recorded overnight. A geologist reviewing the morning data will note its location, depth, and characteristics before moving on. If nothing unusual appears in the pattern, the events are catalogued and the monitoring continues. This is the daily reality of Yellowstone's monitoring network, one of the most comprehensive volcano monitoring systems in the world. More than 40 seismometers are deployed across the park and the surrounding region. 24-hour global positioning system stations track ground position to sub-millimeter accuracy at dozens of locations. Temperature sensors measure water and air temperatures at dozens of thermal features. Tilt meters record subtle changes in the angle of the ground surface. Gas sensors measure the composition of emissions at multiple venting points. Stream gauges track flow rates in rivers draining the caldera. All of this data feeds into a joint monitoring program shared between the United States Geological Survey's Volcano Hazards Program and the Yellowstone Volcano Observatory, a partnership involving the University of Utah, the University of Wyoming, and other institutions. The data streams in continuously, 24 hours a day, every day of the year. The alert level system used for Yellowstone has 4 stages. Normal means background activity with no signs of elevated unrest. Advisory means elevated unrest above typical background levels, requiring enhanced monitoring but no public concern. Watch means escalating unrest with increased potential for eruption, requiring public notification and preparatory action. Warning means eruption is imminent or underway, requiring immediate response. Yellowstone has operated at normal for most of its monitored history, with brief periods of advisory designation during episodes of elevated seismic swarm activity or caldera uplift. The system has never reached watch or warning level. The instruments detect the continuous background of micro-earthquakes, ground breathing, gas venting, and hydrothermal fluid movement that characterizes a living volcanic system. Normal, in Yellowstone's case, involves hundreds of small earthquakes per year, continuous caldera deformation, daily carbon dioxide output measured in tens of thousands of tons, and thermal features that fluctuate in temperature and output with the seasons and with local hydrothermal changes. What the monitoring system is calibrated to detect against that loud background is a signal that rises above it, a sudden escalation in earthquake frequency or depth pattern, an acceleration in ground uplift rate, a sharp change in gas chemistry, the appearance of new surface features in areas previously inactive. The instruments are sensitive, the people watching them are experienced, but the new data from 2025 and 2026 had revealed that the system they were monitoring was structured differently than the models underlying the alert thresholds had assumed. The instruments had not changed. The data they produced was as reliable as ever. What had changed was the understanding of what the data meant, and that understanding was still being updated. Yellowstone gets the most attention. It is inside one of the world's most famous national parks. It sits beneath a wealthy, heavily monitored country with extensive scientific infrastructure, and its last eruption left a geological scar visible across a continent. But Yellowstone is not the only supervolcano on Earth, and one of the others has been showing behaviour that kept volcanologists occupied throughout the first half of the 2020s. Campi Flegrei sits beneath the western edge of Naples, Italy. Where Yellowstone is buried under a remote Wyoming wilderness, Campi Flegrei sits beneath a metropolitan area of nearly 3 million people. The caldera, roughly 8 miles wide, is partially submerged beneath the Bay of Pozzuoli. Apartments and neighbourhoods sit directly on the caldera floor. Campi Flegrei last erupted in 1538, a relatively modest event by supervolcano standards that still displaced thousands of people and reshaped a section of the coastline. But beginning around 2005, the caldera began a prolonged period of ground uplift called bradyseism, a slow rising and falling of the caldera floor driven by hydrothermal and magmatic pressure changes below. By 2023, the ground in parts of the caldera had risen nearly 4 feet since the uplift phase began, the most significant deformation recorded there in decades. Earthquake swarms became more frequent. Authorities in Italy elevated the alert level for the area to orange, the second highest tier in their system, and began updating evacuation plans for the surrounding communities. Campi Flegrei's behaviour and Yellowstone's behaviour reflect the same fundamental class of process. Both sit above large magma systems with significant hydrothermal components. Both show ground deformation driven by a combination of magmatic and fluid pressure changes. Both have long histories of eruptions ranging from minor to catastrophic. The critical difference in terms of near-term risk assessment is that Campi Flegrei shows a sustained, multi-year uplift trend with increasing seismic frequency, a pattern that represents a more definitive escalation signal than the shorter-term, localized pressure event at Yellowstone in early 2026. The comparison is instructive. It shows what genuine escalation in a supervolcano system looks like when it develops over time. The instruments record it. The patterns become clearer with each passing month. The data distinguishes between a system that is actively pressurizing and one experiencing localized hydrothermal changes against a stable background. By that comparison, Yellowstone in 2026 remained firmly in the stable category, with localized signals that warranted careful watching, but did not approach the sustained multi-year escalation pattern visible at Campi Flegrei. The signal at Yellowstone was real. The scale of it was not yet comparable to the level of concern around Naples, but both systems reminded scientists of the same truth. Supervolcanoes are not geological relics. They are active, ongoing processes sitting beneath inhabited landscapes, and the data they generate requires continuous expert attention. In June of 1991, a mountain in the Philippines that had been dormant for over 600 years erupted. Mount Pinatubo injected roughly 5 cubic miles of material into the atmosphere, making it the second largest volcanic eruption of the 20th century. The eruption killed more than 800 people, buried farmland across a wide region in thick ash, and temporarily displaced hundreds of thousands of residents. But Pinatubo also gave scientists something invaluable, because the United States Geological Survey team monitoring the volcano recognized the escalation signals in advance and issued warnings that led to the evacuation of tens of thousands of people before the worst of the eruption. The death toll was a fraction of what it could have been. The scientific monitoring system worked. The warning was given. People moved in time. The lessons from Pinatubo shaped modern volcano monitoring protocols. The combination of signals that preceded the eruption, increasing earthquake frequency, ground deformation, escalating sulfur dioxide emissions, steam-driven explosions from the summit, became a template for what a genuine eruption escalation sequence looks like in real-time data. Scientists studying Yellowstone applied those lessons directly. The monitoring network designed for the park incorporated the multi-signal approach developed in the aftermath of Pinatubo. The alert level framework used for Yellowstone draws on the same escalation pattern logic. If the signals at Yellowstone began mimicking the Pinatubo sequence, the protocols for responding would be triggered. Pinatubo also taught something about the stratospheric effects of a large eruption that directly inform the volcanic winter models applied to Yellowstone scenarios. The Pinatubo eruption injected 20 million tons of sulfur dioxide into the stratosphere. The resulting sulfate aerosol layer reduced global average temperatures by about 0.5 degree Fahrenheit for roughly 2 years. The effect was measurable in global temperature records, in precipitation patterns, and in agricultural output across the Northern Hemisphere. A Yellowstone super eruption would inject an estimated several billion tons of sulfur dioxide into the stratosphere, thousands of times more than Pinatubo. Scaling the Pinatubo observations to that volume produces the volcanic winter projections that appear in every serious Yellowstone impact assessment. The Pinatubo data is the observational anchor for those projections. The climate models extrapolate from it. The lesson that sits beneath all the technical details from Pinatubo is fundamentally about information. The eruption was survivable for far more people than it otherwise would have been, because scientists read the signals correctly and communicated clearly and early. The monitoring worked not just as a data collection exercise, but as an early warning system that translated into human action. That is the goal of every monitoring system watching Yellowstone. The data is not just for scientific papers, it is for the question that matters above every other. How much time do we have? Every powerful force eventually diminishes. Rivers carve canyons and then slow as the land flattens. Storms weaken as they move over cold water. Hotspots are not immune to this logic, and several lines of geological evidence suggest the Yellowstone hotspot may be declining in strength over the very long term. The evidence comes from comparing the 3 super eruptions in the hotspot's history at its current location. The first eruption, 2.1 million years ago, produced a volume of ejected material larger than either of the 2 events that followed it. The second eruption, 1.3 million years ago, was slightly smaller. The most recent eruption, 630,000 years ago, was smaller still. A downward trend in eruption magnitude across 3 events is suggestive, though with only 3 data points, it is far from definitive. A second line of evidence comes from the behaviour of the hotspot as the North American plate has moved over it. In older portions of the hotspot track across Idaho, the caldera complexes burned by the same heat source are deeply eroded. Long since cooled and geologically inactive, the crust over those regions has thickened and stabilized. The volcanic heat that once drove eruptions comparable to or larger than Yellowstone's has entirely dissipated. The hotspot left, the crust cooled, the fire went out. Some researchers argue that the current Yellowstone caldera shows signs of following the same trajectory, just earlier in the process. The shallow chamber melt fraction is lower than models of a vigorously recharging system would predict for this point in the cycle. The deep heat flow, while still enormous in absolute terms, has decreased from levels inferred for earlier periods of activity. The hotspot, in this view, is gradually weakening as it loses energy, and as the continental crust above it thickens over geological time. The opposing view holds that the current low melt fraction reflects a normal position in the post-eruption recharge cycle, rather than a long-term decline. 630,000 years of cooling and partial solidification following the last supereruption would naturally produce a low melt fraction at this stage. The deep chamber supplying heat from below is still active, still connected, still maintaining the system above absolute zero of activity. The data available as of 2026 cannot definitively resolve the debate. The monitoring record covers decades, not the hundreds of thousands of years needed to distinguish a declining hotspot from a normal recharge phase. The geological record of the 3 super eruptions provides a suggestive pattern, but lacks the resolution to confirm a long-term trend. What the debate does clarify is an important limit on any eruption probability estimate. If the hotspot is genuinely weakening, the probability of another super eruption from this caldera is lower and declining. If it is in a normal recharge phase, the probability is harder to assess, but the fuel supply remains sufficient. Current monitoring data cannot tell scientists which scenario they are in. That honest uncertainty, clearly stated by every serious researcher working on the question, is the correct scientific position. The system is large enough, complex enough, and old enough that humility about its future behaviour is the only warranted stance. Assume the monitoring system at Yellowstone detects the beginning of a genuine escalation sequence. Seismic swarms intensify. Ground uplift accelerates across the caldera. Sulfur dioxide emissions spike. A team of geologists reviews the converging data and concludes, with reasonable confidence, that the system is moving toward an eruptive state. How much time would the world have, and what could actually be done with it? The time question does not have a clean answer. Volcanic systems vary enormously in how quickly they move from early warning signals to eruption. Small volcanoes like Pinatubo showed clear escalation over weeks to months before the climactic event. Supervolcano systems, because of their scale, may show precursory signals years or even decades before a full eruption, or they may escalate faster than models predict if the specific trigger mechanism acts quickly. The best current estimate for Yellowstone, based on what monitoring data would be available and what the geological record of precursory activity at comparable systems suggests, is that a genuine warning window of months to a few years is plausible if the escalation follows the patterns scientists have modelled. That window would not be certain, it would be probabilistic, with scientists communicating escalating confidence as signals accumulated over time. In that window, the actions available to humanity range from highly effective to essentially impossible, depending on the timescale. Evacuation of the immediate region around the park is practical on a weeks to months timescale. The pyroclastic flow zone, the area within roughly 100 miles that would be destroyed in the first hours, has a population in the hundreds of thousands. Moving those people with weeks of preparation is achievable with massive mobilization of transportation infrastructure, protecting critical food supplies by accelerating harvest, filling grain storage reserves to maximum capacity, and pre-positioning food stockpiles globally is meaningful if the warning window is a year or more. The world currently operates on tight food margins. Using a warning period to rebuild those margins could reduce the severity of the post-eruption food crisis. Pre-positioning emergency generation, water treatment capacity, and medical infrastructure in regions outside the ashfall zone, so that those regions can absorb displaced populations and maintain function, requires coordinated international action that the current global infrastructure has never attempted at that scale. None of these actions eliminate the consequences of a super eruption. They reduce the worst outcomes at the margins. The eruption itself, and the volcanic winter that follows, cannot be prevented by any technology available or foreseeable. What the monitoring system at Yellowstone does, with all its sensors and data streams and alarm thresholds, is purchase time. Time is the resource. The sensors exist to generate as much of it as possible. every improvement in monitoring sensitivity, every new discovery about the system structure that refines the models, every additional instrument deployed in the caldera contributes to that single goal. The scientists watching the eastern caldera signals in 2026 were doing exactly that work. Reading the data, refining the models, keeping the instruments running. There is a scenario that appears in very few published papers, not because scientists dismiss it, but because it is difficult to quantify, and because stating it clearly requires accepting a level of uncertainty that formal scientific communication handles awkwardly. It sits at the edge of what the data currently supports and what the new discoveries make harder to rule out. The scenario is this: the tilted magma pathway connecting Yellowstone to the broader basin and range tectonic system experiences a sudden increase in flow rate triggered by a major seismic event far from the park. The increased deep supply accelerates heating of the lower margins of the deep chamber. Volatile gases saturate the bridge zone between the deep and shallow chambers faster than the standard recharge models predict. The melt fraction in the shallow chamber rises more quickly than the monitoring system, calibrated on older models, is configured to detect as anomalous. Meanwhile, the ongoing silica deposition in the rock above the cap has sealed enough venting channels in the eastern caldera region that the cap's ability to release pressure is running at reduced efficiency. The system that has been self-regulating for hundreds of thousands of years encounters, for the first time in the monitoring era, a combination of increased deep supply and reduced surface venting happening simultaneously. The ground begins rising faster. The rate of rise crosses thresholds. The monitoring team escalates the alert level, but the models they use to interpret the rate of rise were built before the tilted pathway was known, before the full scale of the deep chamber was understood, and before the hidden earthquake map revealed the extent of channel obstruction in the eastern caldera. The models say months to years. The actual timeline is weeks. This is not a prediction. Scientists are explicit about that. The specific sequence requires multiple coincidences happening together in a system where each individual factor has a low probability of triggering rapid escalation. The probability of this exact scenario unfolding on a near-term timescale is assessed as very low, but the new maps of 2025 and 2026 made one thing clear above all else. The system is more connected, more complex, and more capable of producing surprises than the previous generation of models had captured. Every discovery revealed a variable the older models had not fully accounted for: the deep chamber, the tilted pathway, the hidden earthquake network, the breathing cap. Each one changed the picture. The scientists who built those discoveries into the updated understanding of Yellowstone did so rigorously, with care and precision. Their work made the monitoring system better. Their discoveries gave humanity a more accurate view of what sits beneath one of its most visited landscapes. And their honest conclusion, stated in papers and presentations and monitoring reports throughout 2026, was that a system of this scale and complexity, sitting live and active beneath millions of people, deserves continuous, serious, well-funded attention. The ground beneath Yellowstone rises and falls each day. The cap breathes. The hidden earthquakes trace their invisible paths through fractured rock. The blue pool steams in the morning air at Norris Geyser Basin, a new window into a system that has been building towards something for 16 million years. The sensors are running, the scientists are watching, and the mountain is breathing,